Yeah, thank you very much for the recording. My name is Shaiban Garari, and I'm going to basically convene or chair this session on model development and applications. We have an array of interesting talks and topics. I would like to just mention that we don't have time for question and discussion. Depending on how much time we get at the end, we might be able to discuss some of the questions or have a discussion around some of the topics. However, you can always send your question directly through the chat to the presenter, or later you can contact them if you know of course, their name and the contact information. So I will be very strict with the time because we have quite, sharp 10 minutes for each talk. Without talking too much, it's 11:45. I give the floor to the first presenter, Kevin Shook. He will talk about the development of the prairie hydrology design and analysis product, PIDAP, if I pronounce it correctly. Kevin, floor is yours.
Okay, you can see my presentation?
Yes.
Okay.
Everything's fine.
Thank you. So I'm going to be talking, as Shaiban said, about PIDAP, which is a extension of the work that we're doing in prairie water. The reason for working on this is that there are a lot of real-world hydrological problems on the Canadian prairies for which either there are not any existing tools or the existing tools are not well suited to. And the idea of PIDAP is to use the research work that's been done by the GWF Prairie Water Project to produce a tool that is useful for solving local scale water problems on the prairies. Many problems on the prairies are extremely local. They are very small scales, which are too small to be represented by larger scale models, including the models that we've built for prairie water. And these problems include small scale flooding or the effects of local drainage. Another problem is that local hydraulics are not simulated well by hydrological models. And this can be something as simple as the effects of culverts, or the effects of roads. It also includes human management, gates and pumps, which can have large effects at small scales. And the final problem is that many users require stochastic or return period values, but existing models are deterministic, and drainage regulations in many places are based on return period flows. So you can't get this with existing models. So the idea of PIDAP is that it will provide a data set which can then be used to get answers to local scale hydrological problems. So it's not going to solve the problems, it's going to provide a data set which can be used as inputs to hydraulic models, such as SWIM, for example. And these hydraulic models can then provide answers to local scale questions. The hydraulic models can incorporate complex local hydraulics. This is one of their advantages, which we can't do with existing hydrological models. These models will require skilled hydraulic modelers, though. This work can't be done by end users, such as RMs, unless they have really good skilled hydraulic modeling capabilities. Prairie Water has, as part of its work, classified about 4,000 hydrosheds basins in the prairies, which you can see here. Each basin is about 100 square kilometers, and they were classified into 7 different types based on topography, soils, and vegetation. And the intent is to use all of these 4,000 prairie basins, each about 100 square kilometers. As a large part of the work that we've been doing in prairie water, we've also built a virtual basin model in CRIM for each basin type. So we have created 7 different virtual basin models. And we have been running these models at several different locations, and we've been forcing them with local meteorological station data. And these models are able to demonstrate the effects of climate change and or changes in depressional storage. And it's been shown that these models have a pretty good representation of the average basin responses for their type, whether that's stream flows or the snowpack or the soil moisture. So the idea is to take these models and use them. The FIDAP data sets will consist of time series of depths of rainfall, evaporation, and upland runoff. So this isn't the stream flow. I'm talking about the runoff from the soil produced by these prairie water CRIM virtual basin models. And we're going to run these models for each of the 4,000 basins, each one using the appropriate class of virtual basin model. So each of the 4,000 basins will use whichever virtual basin model best fits it. The CRIM models will be run for as long as durations as possible. We will force them with historical data and future climate simulations. And if we can do these for long runs, the outputs can be used for stochastic purposes. This is the idea, to bridge the gap between deterministic and stochastic modeling. The final step, which will not be done by Prairie Water, will be to use these FIDAP CRIM model outputs as inputs to a hydraulic model, such as SWIM. The hydraulic model will then be run to give time series of local flows and flooded areas. And from these, return period values can be extracted. The useful part will be the users being able to find changes in the return period values. Those that are caused by changes in climate can be estimated by rerunning the hydraulic model using the FIDAP CRIM outputs, which were forced by future climate data sets. Changes in the return period values caused by changes in drainage or human operations are determined by rerunning the hydraulic model using changes in the local parameters. So this is up to the local hydraulic modeler. We've made some progress to date. One of the most important things is that CRIM has been refactored, and so it can now be run on clusters. Because of the refactoring done by people in computer science at Kevin Schneider's group, it now runs between 3 and 5 times as quickly on the same hardware as it did before. All of the virtual basin models have been completed and tested. And use of CRIM with hydraulic models is being validated. So Kelvin Alltrade used CRIM and PC SWIM to simulate the flows and floodings at a culvert and road system. Holly Anand used CRIM and SWIM to model the backwater effects of a culvert on the flows of the water survey gauge at Smith Creek. And Amir Kaibari is working on his MSc with Kerry Mazurek, and he is attempting to validate the flooded areas produced by a hydraulic model forced by CRIM outputs. And we've also selected the gridded climate data set for forcing the CRIM virtual basin models. So our next steps, well, we're currently working with our partners to determine the usefulness of the FIDAP outputs. We're going to do some small scale tests on a few basins. We will then incorporate their feedback into the models. We will also be creating scripts that will allow us to run on a cluster that will allow us to extract gridded climate data and create the CRIM forcing files for each basin, run CRIM, and post-process the data for each basin. And we think that doing a set of runs for about 4,000 basins should take us less than a week once the system is set up. But of course, it's going to take us a while to get the system set up and running. And that's all that I have.
Yeah, thank you very much, Kevin. Really on time. I just want to reiterate what I mentioned in the beginning of the session, is that we don't have question and answer. So if you have any question for Kevin or any other presenters here, please send them your question directly either to the chat or to the email, and then we can continue discussion after all the presentation or during other time. So without further ado, we go to the second presentation. Again, thank you, Kevin, for the presentation. We go to the second presentation, Zhi Zhang. on land surface modeling of wheat growth dynamic in Canadian prairie. G, floor is yours.
Hello, hi everyone, can you hear me?
Yes, perfect.
Thank you very much. Good morning and good afternoon. Welcome to today. My presentation. It's about modeling the dynamic growth of spring wheats in the Canadian prairies. So first of all, I want to acknowledge all these contributors in this work, including my supervisor and Philip and Warren from the Agricultural Water Future Project, and also my colleagues in the National Center for Atmospheric Research for the modeling support in the YMP. So first of all, let's talk very briefly about the motivation, the goals of this study. So here I'm looking at the Canadian prairies, and wheat is the largest staple field crops planted in this region. And it's also a very large, Canada is also a very big exporter of wheat globally. So Canadian prairie is also known as the breadbasket to the world and to this great country. In 2016, the Agricultural Water Future Project set up a few sites of anticovariance fluxes measurement in the cropland in Saskatchewan and Caniston and Glavit. Philip will maybe talk about some of this in his later presentation. But here, for my work, we focus mainly on modeling using the YMP crop model, which was originally developed for corn and soybean in the US Corn Belt. So that our first goal here is to ask, can we adapt the new sets of spring wheat parameters in the YMP crop model, starting from a single site? The next question we're trying to ask is, if we have the single site, how do we transition from the single site to a large regional study incorporating the dynamic of LAI and then a final yield? And lastly, maybe we probably don't have time to cover it today, is how do the final yield respond to high temperature stress in recent decades? So first of all, we can take a very brief introduction to the YMP crop models. So it basically contains three components. The first is highlighted here as the photosynthesis and stomata components, which calculate the carbon assimilation based on the environmental factors, such as radiation, temperature, soil moisture, and etc. And the temperature taken from a daily temperature in the model would be calculated as a heat unit called a growing degree days, GDD. And the accumulation of GDD will be separated into several growing stages within the growing season. And according to these growing seasons, the model will partition the assimilated carbon dioxide, also the carbohydrate, to different parts of the plant's body, including stem, roots, grain, and leaf area index, leaf mass, and convert it back to the LAI, feedback to the stomata subroutine. So the most important variables here will be grain and leaf mass, which we talk about it today. As I mentioned, it was developed originally from corn and soybean, so that we want to adapt the new sets of phenology and photosynthesis parameters for the spring wheat, accommodating the spring wheat feature in the Canadian prairies. So the first step is, let's take a look at the first 3-site year single site study from Caniston site. So we obtained 3 site years. We conduct the 3 site of single site study modeling. So here you see 3 site year of the first row is the growing degree days, GDD. The second row, LAI, and the third row, above ground biomass. I want to highlight that the red dots are from the site measurement. The black lines are the default LAI, which was taken from a monthly climatology table, and the blue lines are from calibrated parameters, and then new sets of wheat modeling results. So what I want to point it out here is that, given also in the biomass, you can see that the model will be able to represent both the LAI and the biomass as compared to the default parameters. However, we miss the specific partition of plants organs because we only have the total above ground. However, there's another part, if you can look at the orange line, that is the model simulated yield grain. And as other crop model might put it into another parameter called the harvested index, which is the grain divided by the above ground biomass to be around 0.4. So our model, despite we don't have much specific detail, but the result fall into a reasonable range compared to other modeling study. So these are for the LAI and biomass. And the next question is to ask, if we improve the LAI, how does the model respond to the latent heat flux and sensible heat fluxes, as well as soil moisture? If we look at the figures on the top here, the improved LAI simulation suggests the higher latent heat fluxes and lower sensible heat fluxes compared to the black default line here, especially if you look at the June, July, August, which is the peak growing season of LAI in the wheat, which is much improved compared to the default simulation. On the other hand, that when you look at the soil moisture, that is the higher LAI will transport higher latent heat fluxes, which in turn demands more water from soil moisture. So in one word, the wheat model acts as a more efficient couplers in the soil moisture, in the soil vegetation atmospheric continuum that is to a dynamic aspect that we expected from this study. And the next step is we want to understand how to transition from the single point simulation to a larger scale, covering the Canadian prairies as well as the US Northern Great Plain. To do that, we need to know where and when these weeds are planted. So here we gather the information from the AAFC annual crop inventory and the US cropscape data, which composed of growing fractions from 0 to 1 in the modeling grid cell perspective. And on the right, we have the Statistic Canada and the USDA sensor data, which collect the planting area for Canada as well as in the US. As for the planting date, we did here 2 simulations. So one is use the most usual date, which is a uniform within one state. We call it the state level planting and harvest. And on the right hand, we have I incorporated a dynamic feature, which shows the planting and harvest date on a dynamic scale, which, for example, the planting is triggered by a 5-day running average temperature higher than 12 degrees, and the harvest is triggered by accumulated GDD higher than 1,500. So these are trying to incorporate the dynamic planting and harvesting scheme. And then we're going to take a look at the results on, first of all, the transitioning to regional LAI. So on the left, I'm comparing an 8 days MODIS LAI time slice. So here you see the 4x4 matrix. So from the usually from the start of May to the end of August. And you can see that the MODIS LAI, I'm only showing the swath of the covering the study region. And the middle is the state level planting and harvesting, where you can see there's a very obvious state level boundary cutoff, usually too early or too late. And we know that that is artificial. And on the right-hand side, we see that the the dynamic planting and harvesting, we expect to have like the greening up in starting from late May, and then start growing the LAI greening into June, peaks in July, and then entering August, and it starts to harvest, which in a large degree reasonably well represents those in the MODIS LAI. And what we want to capture is these gradients that's temperature driving is the earlier in the south and then later in north, both in planting as well as in the harvest. So that is to our expectation that is in the dynamic feature. The next step is, can we model how does the model represents the final yield compared to an observation or census data in the final yield? So here I'm looking at it's also a composed data from USDA and the Statistic Canada. I converted to dry mass grain per meter square. In the middle is the state level planting. As you can see, there's so much overestimated in Alberta, Saskatchewan, as well as in North Dakota. While in the dynamic vegetation, a dynamic plant and harvesting shows a shorter growing season and then reduced high yield biases as in most of the domain. And what is contributing to this high yield biases in the state level, as we can separate them and we see, is usually that we scatter the growing degree, we scatter the duration of grain filling stages on the x-axis and then the y-axis to the final yield. And we see there's a clear almost linear relationship to the longer of the growing season and then the higher yield it will contribute to. And finally, if we constrain the growing season by a more dynamic or a reasonable amount of the growing season, that's the final yield will be, of course, shorter. And finally, that's my conclusions that we adapt a new set of parameters from the single site, trying to improve LAI and turbulent fluxes. And then we transition the model to a regional scale from single point to regional scale and expect to have more dynamic LAI and the final yield simulation. The next step, we will work on trying to incorporate a temperature stress function to represent the impact of the extreme heat wave. And thank you very much. That's all, thank you.
Thank you very much, Yi. We are at 12:05 Central Time. We go directly to the next presenter, Philip Harder, which I think will be a follow-up to this presentation. Philip Harder will talk about improved prediction of crop water use in cold region agriculture using coupled model. Philip, floor is yours.
All right. You can see my screen, but yes, I'm Philip Harder, and I'm going to be talking about some of the work around improving some of the predictions of crop water use in cold regions agriculture. And this is work that I've been doing with Warren Helgeson and John Pomeroy through the Ag Water Futures project. And so, yeah, thanks, G, for setting it all up. So it gets rid of a lot of things I need to talk about. But to set the stage, sort of big picture, when we talk about Canadian prairie agriculture, we really need to talk about the water and ag interaction. So on the prairies, it's this huge area of Alberta, Saskatchewan, Manitoba, and within it, about 50% of this area is annually dryland cropping systems. And this is an area that is typically under water stress. Obviously, there's variability in that. Right now, Manitoba is underwater and Southwest Saskatchewan still super dusty. And so within all of this really intense climate, we've had this development of a very successful agricultural industry, which has been very adaptive to this extreme climate. The figure on the bottom right, the blue is precipitation historically and projected into the future at Saskatoon, while red is our average Saskatchewan spring wheat yield. And so while yes, we have a significant correlation between the amount of water available in as indexed by annual precipitation with our annual variability in crop production, you can see that crop production has nearly tripled since the early 1900s. And this is because we've been very successful at adapting management practices, going from summer fallow to zero-till systems, which are much better at soil and water conservation, but also crop breeding and all those other aspects that have come together to make prairie agriculture so successful. But at the same time, it is highly subject to a variable climate, specifically prairie hydrology, which is quite complicated. So in the winters, we have snow accumulation, and then comes snow melt. We have snow melt interacting with frozen soils to determine our moisture recharge. And then once we get into the summers, things are hot and dry, and we're in a moisture limited state. So there's a lot of factors that are going on. So what can we do to understand this and possibly increase some of the resilience of the system moving forward? So a big part of our work has been looking at trying to quantify the prairie crop water balance. And so we've got field observations going back to 2015. And here I'm presenting the growing season crop water balance. So typically evapotranspiration is equal to precipitation plus a change in soil moisture. over a seeding to harvest interval. And so we've got a number of sites near Saskatoon, and we tried to go out independently and directly measure every one of these components. And not surprisingly, these don't balance. So on average, evapotranspiration is this red part of the graph. Rainfall only comprises 62% of the water that's being transpired by our crops. On average, 12% of it, also 12% of the crop water use comes from a change in soil moisture. Then we have this other part of 26% on average, which is unaccounted for. And we can make all sorts of speculation on what's going on in terms of our sample design and spatial variable hydrology. But long story short, on average for this interval, 38% of our crop water use is really provided by non-growing season hydrology. And this is coupled through our soil moisture reservoir. And there's a lot that's going on here. But at the end of the day, when we start putting numbers onto our wintertime water balance and looking at sort of the efficiency of how much snow we catch in our stubble versus what falls, versus how much water actually makes it from our wintertime inputs into the soil, we see very large inefficiencies. And so this might be a place where we can play around and improve some of the practices to increase crop productivity moving forward. So conceptually, when we want to talk about crop water ag interactions, we need a bit of a conceptual model. And so if we go over the course of the year, we have snow accumulation in the wintertime, comes to snowmelt partitioning. So we have a certain amount of that actually makes it into the soil, some of it runs off. And then we've got this period of time where we've got springtime soil evaporation, where we lose some of that soil moisture. And then when we have growing season sort of kicks off, now we have a huge increase in evapotranspiration, which typically uses up all the precipitation and soil moisture that's available. And then afterwards, we've got the soil evaporation component, which further dries out soils. And so we have all these little interactions that ultimately give us, a yield response. But the problem is we don't really have a good model that puts it all together. So a big part of the work recently has been to come up with this cold regions agrohydrology model, which is in a nutshell, a process-based model that can actually directly couple these things. And so for the wintertime processes, we're using CRIM, which has been talked about previously at this meeting. And then we're coupling it with a crop growth model, AquaCrop, come the summertime, and coming up with a scheme where we are passing soil moisture between the two, and then also stubble heights and densities to get these feedbacks between the hydrology that happens in the winter and the crop growth that happens in the summer. I won't talk more about CRIM, but AquaCrop is a bit new for some of the variable crop types on the prairies, and so needs to do a bit of validation and calibration on this to make sure that it works. And so in a nutshell, AquaCrop is a simple water limited crop growth model. So simple means we have less variables, but 24 variables that we potentially can play with, leads to a lot of issues of equifinality. But within all of this and using a VARS-based approach, we've gotten to the point where we can do fairly well on simulating biomass. I'll refer you to the 2021 corn, 2021 situation where we had serious drought. We have 1 year of corn data to work with, field corn, and clearly we're not doing well there yet because that was an extreme scenario. But for the most part, we are able to capture biomass, we're able to capture evapotranspiration, as well as soil moisture that I'm not showing here. Because we need to have confidence that what water we put into our model actually will generate the appropriate sort of yield or biomass response. And so with this framework set up, we can start asking the question, well, what about a stubble height crop growth interaction can we quantify? So conceptually, if we increase stubble height, we'll get more snow, which because we have less blowing snow transport and sublimation. With more snow melt, we have a possibility of more soil moisture recharge. Not necessarily, but for the most part, that is what will happen. As well, growing season and evapotranspiration should increase because we have more soil moisture available, and therefore we should have more productivity. So we put all this together in this CRAM model, and let's put some numbers to it. So using some data from near Saskatoon, 2018 to 2021. We have a barley crop, and let's say we can prescribe stubble heights of 5, 25, and 50 centimeters. And we can very quickly see that we have nonlinear feedbacks. Some years we have a bigger response than others, largely depending on antecedent soil moistures, as well as the amount of snowfall in the winter that could, are we even able to fill up the stubble height capacity to resist blowing snow.
So Philip, we have 1 minute if you can back it up.
Yeah, so basically, we can start simulating this crop hydrology biomass response. There's a couple gaps in all of this. Soil evaporation is a fairly weak point of the model because there's a snowmelt, post-snowmelt period, which is really important. Surface residues can be rather challenging to capture in this at the moment, and there's some feedbacks that we need to start thinking about. But moving forward, we're going to be applying CRAM over the prairies to look at climate change impacts on crop water use and productivity, and also start considering how we can use stubble and surface management practices to optimize water use efficiency. And yeah, I'll leave it there at this point, but this is a work in progress and lots of potential outcomes to come.
Thank you very much, Philip. Very interesting talk. We are at 12:15, right on time. We go to the next presenter, Jihua He, modeling the effect of climate change on snowmelt, soil moisture, and stream flow generation for the Canadian prairie. Jihua, the floor is yours. You can share your screen. Yes, we see your screen.
Okay, thank you, Sharon. I'm Jihua He, and I'm a postdoc working for Professor John Palmer and Dr. Chris Spence. And just follow up Karen's presentation today. So I may focus to introduce some results from our modeling work in the Prairie Water Project. And also I'm appreciate for all the contributions from our co-authors in this presentation. So as you will see from Karen's presentation, we have divided interprairie into 7 classes. So here, this map shows the locations of the classes, and also the locations of the AHCCD stations I have used for the meteorology input to foresee the model. So they are include the Meetings Head station in the west, Swift Current, Regera, and the Yorkton station in the middle, and the Brandon station, William Picker station in the east. So this figure to show the concept of the virtual basin modeling approach. So we are using the common land cover types in the prairies, including cultivated or cropland and the grassland and the wetland as the HRUs to represent the land covers in the green model. So this figure also shows the routing orders of the different HRUs in the model. And then we are using 46 HRUs to represent the wetland complex in all the classes. And we have some results for the evaluation of the virtual basin-based green model in the prairie basins. So this figure shows the performance in the simulation of stream flow in the 7 classes. So we can see the red colors are for the simulation, and the black color for the black color is for the observations. So we can see the simulated range of the annual stream flow in general agree with the range of the annual stream flow from the observations in most of the classes, like interior class in the Swift kind of station and the soil slope inside, and also such as the major river valley class and the source Manitoba classes. And the simulated monthly stream flow indicated that there are very small stream flow in the summer seasons and autumn, winter. And the stream flow mainly focus in the May season from March to May. So that is also inconsistent with the observations. And we are using the elasticities to represent the sensitivities of the hydraulic variables to the precipitation and the temperature changes. So in this figure, the x-axis is the percentage changes in precipitation, and the y-axis is the percentage changes in the SWE and the melt runoff. So in terms of the slope, we can see the SWE show the comparable sensitivities to precipitation increase in the HEG and the PhD class. But for the melt runoff, we can see the decreased sensitivities from the west HEG to the east PhD class. And this also happened to the response to temperature warming. And in this figure, the x-axis is the degree changes in the temperature. And in terms of the slope, we can see the decreased slope from the west HEG class to the east PhD class. Also, I compared the sensitivities of the other slow processes like sublimation and infiltration. So we can see even the flexion changes in the slope flow is the same in these two classes. But the magnitude differ a lot in the two classes. For example, the PhD class showed a much larger magnitude changes in the slow sublimation and the slow melt infiltration. And also I combined the sensitivity of soil moisture in the cropland HRU in these two classes. So for the soil moisture in the upper layer soil, we can see the changes are very small in both the HEG and the PhD class. But in the lower layer, we can see the changes in the soil moisture is larger, especially in the PhD class. The percentage changes can be at around 50% in response to 20% in the precipitation. And also the same situation happened to the response to temperature warming. So we can see very small changes in the lower upper layer soil moisture, but much larger soil moisture changes in the PhD class compared to the HEG class. Also, when we investigating the combined effect of precipitation and temperature effect on the soil moisture, we can see the decrease in the soil moisture caused by temperature warming of 6 degrees can be compensated by the increase caused by precipitation increase of up to 20% for the upper layer soil moisture. But for the lower layer soil moisture, the precipitation increase of 10% is already enough to compensate for the decrease caused by the temperature warming of 6 degrees. And this figure shows the sensitivities or the responses of streamflow and evapotranspiration to the precipitation changes of 20% in the middle futures. So we can see the PhD class show the larger deflection changes in the streamflow of around 160%. And the South Manitoba class show the larger magnitude changes of around 96 millimeters. And with the HEG class show the larger deflection and the magnitude changes in the parallel evapotranspiration. So when we check the response of the streamflow and evapotranspiration to temperature warming of 3 degrees in the futures, we can see the HEG class show the larger deflection changes in streamflow, and the South Manitoba class in the east show the largest magnitude changes. And also we can see the South Manitoba class show the largest deflection and the magnitude changes in the prairies. The flux changes can range from 2% to 7% in all the classes. So then we have the conclusion here. So those slow processes such as the accumulation and the melt runoff show the decreased sensitivities to precipitation or temperature changes from the west prairie to the east prairies. And then with the temperature warming of 3 degrees in the middle future, the peak SWE will decrease by 20% to 48% in the prairies. And this cannot be compensated for the precipitation increase of 20% in the middle future. And the soil moisture show that increased sensitivities to precipitation or temperature changes from the west to the east, especially in the South Manitoba class, except for the South Manitoba class. And with the temperature warming of 3 degrees in the near future, the soil moisture in the cropland will decrease by 12%, and this can be completely compensated for if precipitation increased by 15%. And the stream flow in the South Manitoba graph show the largest magnitude changes in response to precipitation or temperature changes. This is partly due because of it has the largest effective drainage and reflection in this class. And with the temperature warming of 3 degrees in the near future, the annual stream flow will decrease by 12 to 49% over the prairies. And the precipitation increase by 8 to 50% can compensate this decrease in the stream flow in the prairies. So yeah, this is my presentation. Yeah, thank you.
Thank you very much, Gilles. And thank you, the presenters so far, for being really on time and keeping the presentation in 10 minutes. I really appreciate that. We go directly to the next talk by Holly Anand on the influence of wetland management and climate change and the hydrology of the agricultural catchment in the Canadian Prairie. Holly, yes, we see your presentation. Floor is yours.
Excellent. Thanks very much, Siobhan. I hope everyone can hear me today. It's nice to see familiar names, if not faces, in the crowd. So just nice to be with everybody. Yeah, the title of my presentation today is The Influence of Climate Change and Wetland Management on the Hydrology of an Agricultural Catchment in the Canadian Prairies. And this is work out of my recently defended PhD thesis with Dr. John Pomeroy and Howard Weeder. So the background on why this study was important to me is that the Canadian Prairies is a wetland-dominated landscape, and these wetlands provide important ecological services for our communities, but that they're often drained to support agricultural expansion and intensification. And in recent years, we've seen some increases in streamflow volume at different locations across the prairies. And on top of that, there's been a shift in the climate regime to more rain on snow events or summertime precipitation, extreme rainfall type events causing increases in streamflow. So the real question then comes down to, is it climate change? Is it agricultural drainage? What can we attribute these changes to, and look further into that? So I used a case study of the Smith Creek Research Basin. Some on the call would be familiar with Smith Creek. It's located near Yorkton, Saskatchewan, and it was heavily instrumented by the Centre for Hydrology from 2007 to 13. Has a Water Survey of Canada gauge, has wetland inventory data, as well as LIDAR and crop use data and all that good stuff that helps us build hydrological models. So I put together a conceptual model of how I wanted to build this prairie hydrological model. I don't want to belabor these things, but obviously we need to be able to simulate blowing snow transport and snow accumulation and frozen soils through the winter period, then infiltration of snowmelt into frozen soils, as well as the all-important depressional fill and spill runoff that occurs in that wetland-dominated prairie environment, as well as then crop growth through the summer period, and infiltration as necessary or triggering that depression fill and spill response when required. Another important component of the model that I wanted to consider was also representing the network of ditches and roads that exist in our agricultural landscapes on the prairies. So I put together a CRIM model that I know everyone's familiar with. And I linked it with I took a novel approach here and linked it with a simple storage reservoir using the stormwater management model as well. And that linkage was to better represent culvert restricted flow throughout the basin. And that's something I can talk more about another time, but today we're going to focus on the model results. So several different HRUs, again, having the conceptual network of 46 wetland HRUs that Kevin and John helped develop years ago as that spill and fill runoff simulation in the prairies. So then I ran the model with outputs from the bias-corrected outputs from the WRF model. For the current or control period is the WRF control, and then the pseudo-global warming simulation into the future climate period. And that's a perturbation under RCP 8.5, or the worst case scenario future climate model. And WRF runs at an 4 kilometer resolution with 1 hour time step, which was great to use with CRIM and with our process-based hydrological model. And then I developed a series of wetland drainage and wetland restoration scenarios. And these would be from a recent or 2008 wetland inventory that linked with the LiDAR data and the model setup that I had, using that as the current or recent period. And then draining wetlands of incrementally larger sizes of 4,000, 20,000, and 40,000, which would be an acre, 5 acres, and 10 acres, up to draining all the wetlands. And then for some restoration scenarios to increase the wetland area fraction up towards a historical maximum that was related to the crop inventory data or air photos that we had from a historical period. So first, just on the projected warmer and wetter future for this period, was that what you're looking at here on the left is increases in daily temperature of about 5.5 degrees Celsius from current to future period. That's from blue to red lines. And then on the bottom left is the increase in precipitation of 44 millimeters. These are mean values across the 15-year model period. Then the model outputs on the right here are the bunch of smaller squares. So simulated rainfall was up 75%, 75 millimeters, snowfall decreasing 32 millimeters. We saw a slight increase in actual evapotranspiration and a decrease in sublimation due to the lower snowpack. Streamflow we'll talk about next, but some decreases in pond depth and a wider range of soil moisture into the future period. Just to note, the shaded areas on these graphs that I'm going to show are 1 standard deviation from the mean. And so the wider the shaded area, the more sort of inter-annual variability there is throughout the 15-year model period. So when we get into the streamflow simulation, then the mean annual streamflow volume is projected to increase, and it's really driven by more extreme summer rainfall events in the future period. So on the left here, we're looking at mean daily streamflow hydrograph, and in the spring period, we see a decrease in peak discharge of about 34%. And then in the summer period, peak discharge increasing drastically at 161%. And that's really driven by a few substantial rainfall events in the future model period, or future climate period, sorry. And then the mean annual cumulative streamflow is on the right. Here we see that increase in cumulative streamflow volume of about 26%. And there again, you see that wide shaded area in the future period having that extreme interannual variability projected into the future period. So then layering over top of that, looking at the influence of various wetland management scenarios and finding that there's an approximately linear relationship that came out of Smith Creek between the wetland area fraction remaining in the basin and the percent change in cumulative annual streamflow volume. So on the left of the picture you're seeing here on the y-axis, you'll see a change in cumulative mean annual streamflow volume, and on the x-axis is the wetland area fraction remaining in the basin. So the blue line here is the control period, or the current climate scenario, and we see as we decrease wetland area fraction or drain wetlands, mean annual streamflow volume is increasing, and as we move to the right, or restoring wetlands, then mean annual streamflow volume decreases. And that's all compared to the recent or 2008 period. So the jump up then is that same relationship, but in the future period. And the important part of this graph, you'll see arrows pointing down to the zero axis here on the left and right. And the one on the right is crossing, where the red line crosses the zero, is the point at which restoration is needed, wetland restoration is needed in the future climate period to restore streamflow into the current range that we're currently experiencing, that mean annual streamflow volume. So that would sort of be the critical wetland restoration point for Smith Creek. And on the left, drainage past about 9% wetland area fraction remaining under the current climate could induce climate change type changes in streamflow. Then quickly, I wanted to look at what the influence of the wetland restoration was on peak flows. So on the left, we're looking at spring peak discharge, and on the right, we're looking at the summer peak discharge. And these graphs now follow the same principle as what I discussed on the previous slide. So I want to bring your attention just to the slide on the right, the figure on the right, where wetland restoration to the historical maximum level was not enough to offset the projected future increase in peak discharge in the summer period. So the red line on the right doesn't come back down to cross the zero axis here in the summer peak period or peak discharge, indicating that full restoration was not enough to offset changes in peak summer discharge. And so there will need to be other emergency management strategies developed, maybe to help deal with infrastructure damage or the other kinds of things that can result from extreme projected summer precipitation in Saskatchewan, or the prairies in general, I suppose. So then just quickly, the conclusions out of this, we are finding that the projected future climate period from the WRF simulations at Smith Creek saw a 5.5 degree increase in temperature, 75 millimeter increase in rainfall, a decrease in snowfall, but more extreme events, particularly summer rainfall extremes, that leading to an increase in streamflow volume, that's mean annual volume, decrease in spring peak discharge, and some major spikes here, 161% increasing in summer peak discharge. And the role of wetlands, wetland management in that is that the change in mean annual streamflow volume is about 3.5% per percent of wetland area fraction change. So that 3.5% change in streamflow volume with response to every single wetland area fraction change. And that restoration was good, wetland restoration was good for decreasing or offsetting mean changes in future streamflow volume, but that wetland restoration was not enough to offset changes in peak summer discharge. And thanks for your attention. Feel free to reach out if you have more questions or want to talk about this research. Thank you.
Yeah, thank you very much, Hadi. Very interesting presentation. I see there is a discussion going on in the chat of the past presentation, which is good. So let's see if we have time to discuss that further at the end of this session. We go to the next speaker, Chris Marsh. Chris will talk about large extent snowdrift resolving snowpack simulation across the Canadian Cordillera. Chris?
Awesome, thank you very much. You can see everything all right?
Yes, everything.
Fantastic, thank you so much.
Yeah.
Yeah, so I'm Chris Marsh at the Center for Hydrology at the University of Saskatchewan. Just apologies for no webcam today. This computer doesn't have one. So the motivation here is the water models that we use really need to account for the substantial spatial and temporal heterogeneity and the mass and energy fluxes present. And this is especially the case in the mountains. So this is reflected in the figure on the right, showing this heterogeneity in snow cover in the mountains. Blues are more snow, the yellows are less snow. So you can see there's a lot of spatial variability. And of course, the spatial variability evolves with time throughout this season. So this heterogeneity, it really motivates the use of snowdrift permitting scales. These are the scales where we can start to explicitly simulate the blowing snow processes, the mass redistribution that leads to cornice formation, avalanching, sublimation. And this is discussed more in the V&A 2021 paper. So estimating these spring snowpacks for really large areas over 1 million square kilometers is critical for quantifying the late-lying snowpacks that are going to be providing those spring runoff events. And being able to do this in the really complex topography of the mountains is really key for the mountain headwater basins. So to do this, I'm using the Canadian Hydrological Model, CHM. Just going to quickly go over it just in case it's a bit new to some people still. So it represents the topography using a variable resolution triangular mesh. This variable resolution is conditioned on topography, soils, vegetation. So the idea is you have smaller triangles, so more spatial resolution where you need it. For example, along boundary transitions between vegetation and non-vegetation, along complex features like ridge lines. And what this allows you to do is have a really large decrease in the total computational and data demands versus traditional rectangular gridded models. CHM includes a lot of algorithms for downscaling meteorological data and includes a lot of process representations that are accounting for the slope and aspects of terrain shading, accounts for the variable wind fields, gravitational redistribution due to avalanching, blowing snow. So that's this redistribution and the sublimation thereof, snow interception and sublimation from forest canopies, and an energy balance snowmelt model, which is then of course impacted by all of these processes. So to go over kind of the model setup, the model domain here is we're going for a large extent snowpack modeling that explicitly is including blowing snow at that snowdrift permitting scale of about 50-meter minimum length scales. And so representing this with the variable resolution triangles leads to a substantial reduction in the total computational elements. And so the underlying rasters that the unstructured mesh is derived from has 3 billion raster cells. So we're able to reduce that multiple orders of magnitude to 34 million triangles. And that's using an elevation, canopy, and water to condition where all the triangles are. And this is going to be over an entire area of 1.3 million square kilometers. The meteorological forcing is downscaling the high resolution deterministic prediction system, HRDPS, from Environment and Climate Change Canada at 2.5 kilometer spatial resolution at a 1 hour time step for the period of October 2020 to June 2021. And so, like I said, this is this full cold regions winter process representation. So blowing snow sublimation, avalanching, canopy interactions, and an energy balance snow model. And for these simulations, we're using about 800 CPUs for about 20 hours of wall clock time. So to be able to solve these problems, there's been a lot of innovations I've had to do in some of the process representations around the blowing snow, but there's also a lot of technical innovations that had to be done. And this is where key collaborators like Raymond Spiteri and Kevin Green have been really, really key in helping, where we can really bring in better numerical methods and better high performance computing methods to be able to really take advantage of the computing resources we have. So just to really be very clear here. So to do these types of simulations requires high performance computing paradigms and process representations that complement that. So one of the ways we've done this is implement a new domain partitioning scheme. I'll describe that a bit later, but it's how we split the domain across all of the computers that are participating in the simulation. And we're doing that with the message passing interface MPI. Because the domain is split across multiple computers, we have to be able to pass information back and forth. And so I needed to write a new MPI compatible version of SnowSlide, which is the avalanching scheme that I use. So this is a parallel scheme. It's a massively parallel scheme that tracks mass transports across these domain partitions. We've also done a lot of work to decrease the memory footprint. And so we can have more processes per compute node. So we can have a faster simulation time. And then the blowing snow model that I'm using is the PBSM 3D model that I developed, derivative from the PBSM model from Pomeroy et al. And so we're solving this as a linear system using the very high performance Trillinos solver. What this essentially allows us to do is shown in the right, where as we add more CPUs, more computational horsepower to how we're running CHM, we can dramatically decrease the runtime. So we're seeing very good scalings. It's near linear. So as we double the available number of CPUs, this halves our total runtime. So this is an example of the domain partitioning. It's kind of like, oh, this is not that difficult. This is actually kind of a key point in being able to harness all of the high performance computing resources to be able to do these simulations quickly. And so we can actually, in the near term, do more near real-time simulations. So I'm just showing my snowcast domain as an example. This is a few 100,000 square kilometers. On the left is the domain shaded for elevation, and on the right is shaded for the domain's partition. So every color goes to its own computational process running on a node in one of our high-performance clusters. And these look like basins, but they're not. They're actually carefully constructed regions that limit the amount of communications between the different MPI processes. So this allows the model to run faster and gives us a bit of load balancing. So this is kind of a key tricky thing that has led to a lot of innovation, being able to run the model quickly. So going back to some of the processes here. So a key challenge for water modeling in the mountains is forcing the model with a realistic wind field. So this is not only wind speed, but also the wind direction. So capturing the channeling around the ridges, down the valleys. These are the formations that lead to cornice formations, leads to avalanching. And so it's critical to get right for a blowing snow model. So I've developed a tool with Vincent Vionnet called Wind Mapper. So it's a model agnostic Python library that allows you to produce wind speed up maps using a CFD model. In this case, we're using Wind Ninja. And then we've also coupled this with the WindStrol et al. 2002 SX parameter to identify leeward recirculation zones. So I realize that's all a bit quick, but essentially what we're looking at is we're taking something like the raw HRDPS field, which is the uncorrected wind field figure, and we're turning it into something like the corrected wind field on the right. So we're getting that valley channeling, we're getting those ridge speed ups, the leeward decreases in velocity or in speed. And this is done very, very quickly at runtime. And then we can also extend this approach to very large spatial domains, those multiple million square kilometers, which is critical for this type of an application. So we're going to be evaluating the results of the model against snow-covered area derivative from Sentinel-2 data that's rescaled to 150 meters. And so this is visible band. Cloud, water, shadow forests are masked out. Corresponding CHM output is also masked out to match. Because it's a really large domain and because of the satellite passes, we don't have satellite information every day. So this is kind of aggregated to a week. So just kind of an example of that spatial variability in our satellite acquisition. So the results are shown here. The domain coverage of the satellite imagery is in the top. The snow-covered area from CHM is in blue. Snow-covered area from Sentinel imagery is in orange. And then just kind of an example of the images along the bottom. So we can see very good close agreement. These will have an R squared of 0.84, sorry. So a lot of really good correlation in both the amount of snow-covered area.
I would appreciate if we can wrap up here at 45.
Yep. And in the temporal heterogeneity, or in the temporal, sorry, and in the temporal progression thereof. So this is just an example of what that simulation looks like. Deep purple is more snow, and then the whites and the grays are less snow. So you can see there's a lot of temporal variability that we're able to capture with that. So it's tying this up. So it's the first simulation of snow redistribution at a snowdrift permitting scale over this large of an area. This is due to significant improvements in high performance computing in CHM. And we're seeing about 83% of the pixels between CHM and Sentinel-2 observations matching. So I'll leave the next steps there, and thank you very much.
Thank you very much, Chris. Sorry, I know that I interrupted you during your presentation, but we were after 45 minutes. So we go quickly to the next presenter, Okan Aygun. He will present us about the predicting water futures in Central Asia using a hydrological glaciological land surface model. Yeah, we are actually changing the domain, so we go to the Asia now. Okan, floor is yours.
Thank you, Shervan. Do you see my screen well?
Yes.
Perfect.
That's excellent.
Hi, everyone. My name is Okan, and I'm a postdoctoral fellow at the Cold Water Laboratory of University of Saskatchewan in Canmore. And today I'm going to present some results from our ongoing work on predicting water futures in Central Asia. I would like to acknowledge my co-authors shown here. The project is a part of the Global Water Futures Water Prediction Initiative. Our objective is to contribute to advancing to modeling capabilities to address pressing societal needs in Central Asia, namely the Aral Sea Basin, which consists of the drainage areas of the two major rivers, Amu Darya and Sir Darya, which has in total around 600,000 square kilometers of drainage area and shared by the Central Asian countries. Among these river basins, the focus of this presentation is Sir Darya River Basin. Sirdarya River descends from the glaciated high mountains and crosses a semi-arid region to the Aral Sea. The drainage area of the river basin is around 300,000 square kilometers, shared by 4 Central Asian states, while the upstream states of Kyrgyzstan and Tajikistan desire to employ water resources for hydropower production. The downstream states, Kazakhstan and Uzbekistan, wish to continue practicing irrigated agriculture, particularly cotton production, which actually causes water conflicts in the region. Next, due to the over-allocation of water, the Aral Sea, which was used to be the 4th largest lake in the world, has been drying up and shrunk by about 85% since 1960s. Yet the projected glacier losses and snow shrinkage resulting from climate change will likely further intensify the water stress in the region. And the impacts to the hydrological cycle resulting from climate change in the region have not previously been diagnosed using physically based hydrological models that can resolve mountain, snow, and glacier hydrology. So this study aims to assess the impacts of projected climate change on the hydrology of Sirdarya River Basin. In this project, we have used a mesh modeling platform, which is the Hydrology Land Surface Scheme of Environment and Climate Change Canada's Community Environmental Modeling System. Mesh uses the Canadian Land Surface Scheme for the vertical exchanges and generation of lateral fluxes, and the routing of subsurface and subsurface water movement is performed using WATROF, and the stream flow is routed through river channels using WATROT. It is suitable for cold region catchments due to its ability to simulate cold regions' hydrological processes, and it requires only restricted parameter calibration due to its physically based nature. Due to the lack of observational data across the Sirdarya River Basin, we first set up a mesh model for the Ala-Archa River Basin, which is a headwater basin located at the northern edge of the Xianshan Mountains in Kyrgyzstan. The river has a drainage area of 300 square kilometers, 15% of which is dominated by the glaciers. And the basin is the major water source for the capital city of Kyrgyzstan, Bishkek. And for the model setup, the mesh model was driven by ERA 5 and EM Earth forcings over the 1991 and 2010 period. And we transferred most of the model parameters from the previous mesh model applications in Western Canada. Here we show the model performance of the mesh Ala-Archa model. Looking at the upper left figure, the mesh Ala-Archa model performs well on predicting stream flow with Klingupta efficiency scores above 0.9 over both calibration and validation periods. And the bias is less than 1% over the whole simulation period. As shown in the lower left figure, the simulated basin average snow fraction was compared against the process NOAA advanced very high resolution radiometer daily images over the snowmelt periods for the historical period. The simulated snow cover area was found to be matching well with the satellite images for most of the years, while showed some visible deviation from the satellite snow cover area in some years, such as 2006 and 2007. And uncertainty of the satellite data could be one of the reasons for the deviations when looking especially at the sharp increases during the melting season. The simulated snow depth was found to be also in agreement with the observation data, although for a short period, as shown on the lower right figure. Next, what we did is we scaled up and built a mesh model for the entire Sirdarya River Basin, which is about 300,000 square kilometers, and glaciers occupy about 2% of the basin. Using the Merit Hydro Dam, the basin was delineated with the main outlet using a rectangular latitude and longitude grid with a special resolution of 0.125 degrees, which yielded 2,200 grids. And slope aspect and land cover classification yielded about 11 group response units. The modeling concepts and parameters were transferred from Alarcha mesh model, and similar to the Alarcha, the mesh Sirdarya model was forced by ERA5 and EMOD. Next, in order to find out the impact of future warming on the basin hydrology, we used the KNMI Climate Change Atlas to determine the seasonal warming in the region for the 2081-2100 period, using IPCC-R5, CMIP5 subset based on RCP 8.5. Looking at the mean of the projections for the seasons, there's a projected warming by 4.9 to 5.9 degrees depending on the season. And here are the seasonal precipitation projections for the region using the same subset based on RCP 8.5. Looking at the mean of the relative precipitation changes, the precipitation is projected to be changed between -10% and 20% depending on the season. And in order to evaluate the impact of future climate on the hydrology of Sirdarya River Basin, temperature and precipitation forcing data over the historical period were seasonally perturbed using the outputs of CMIP5 R5 based on RCP 8.5 during the 2081 and 2100 period. Here are the projected changes in annual precipitation, snow-water equivalent, and stream flow at the basin outlet. As shown, figure 1A, next to the decline in the total precipitation, the snowfall ratio is projected to decline by 50% compared to the historical period. The figure B illustrates that the average peak snow-water equivalent declines by 45% from 100 to 55 millimeter, and the snow cover season shrinks by 3 months. Looking at the changes on mean stream flow in figure C, the peak flow declines by 35%, and it advances 1 month from mid-June to mid-May for the 2081-2100 period compared to historical conditions. And the projected decline in snow accumulation and glacier loss can cause a decline in summer flow by 50%, which is critical for the irrigation in the region. And as shown in figure, the annual flow is projected to decrease by 45% for the future period compared to the recent period.
Yeah.
In conclusion,
we are past time. Okay.
Yeah, I'm concluding. Coupling reanalysis products to physically based hydrological models can provide credible simulations in high mountains, and modeling concepts, setups, and parameters can be transferred from research basins to high mountain river head basins and downstream basins around the world. And results for the Sirdarya show significantly reduced future stream flow under climate change, primarily due to reduction of seasonal snow cover, secondarily due to deglaciation, which would lead to an increased tension over water shared in the region and downstream between upstream and downstream countries, as well as further drying of RLC. And thank you. This is my contact information. If you have any questions or comments, you can reach out to me.
Thank you very much, Okan. We go directly to the next presenter, Apurva Das. I think his presentation is recorded and Carl will play it. Carl, are you here?
Sure, I can play that. Can you hear me?
Okay, excellent. Yeah. Yes, excellent.
Okay, hang on.
I just read the title of Apurva's presentation, which is Application of Machine Learning Approaches in Ice Jump Flood Forecasting and Prediction.
You can see that okay?
Yes.
Okay, I'm going to play it now.
Excellent, thank you. I think I'm not hearing anything, but.
Pardon me, you can't hear it?
At least I'm not able to hear it now.
I wouldn't know.
No, maybe it's the issue from my side, but yeah.
Someone else can see in the chat if they can hear it.
Yeah, there are other people who can't also hear. No.
Can't. Oh.
Cannot, yes. So some people say they can hear.
Some people say they can hear. Oh,
yeah.
Man.
Maybe, I don't know how that is, but maybe you can just talk over it. I mean, if.
Yeah, okay. So ice jam is a stochastic process, yeah. It's the problem with ice jam flooding, it's very difficult to see it coming. It can be very flashy. The rise times can be very, very quick, yeah. And that makes it a little bit challenging for emergency response. And these floods can cause a lot of damage, yeah. So a lot of damage that ensue from them. Let me just move this up a bit. So what we're looking here now, there's actually 3 types of seasons for jamming. It's usually we have the freeze up, and one that's most very dangerous in most rivers in Canada is the springtime breakup as well, the ice jamming that occurs through that. But here we want to look more at the midwinter breakup along rivers, yeah. And we're applying hydrological modeling and machine learning models to determine sort of propensity for midwinter breakup, and looking also in the future, future climatic conditions, what the propensity for midwinter breakup can be. Yeah. So the study area that we're looking here is the St. John River. The St. John River is actually a regulated river. There's 3 dams here. There's one over here called Mactaquac, and then here is Beechwood, and then there's one over here at Grand Falls. We're going to concentrate more on the headwater part here. It's more the larger part here, or the natural flowing part upstream of Grand Falls. And key gauges that we have here, here's Grand Falls, and one would be Edmundston right here. And we also have a flow gauge here at Fort Kent, you can see over here. Yeah. Now what's important is sort of just how the flow, the hydraulic conditions have changed over the decades. Actually, we have here 2 time series, a 40-year period, one from 1941 to 1980, and the black here. And you can also see 1981 to 2100 here as well. One thing you'll notice is that the stream flows the high flows have occurred earlier. A lot of these too are also, we're getting more rain on snow events here, same with these here. And then during the winter as well, we're also getting a tendency to higher flows or higher peaks as well. So generally a little bit more flow now And this is reflected also on the number of ice jams that are being recorded at Fort Kent, actually, along the St. John River. So you can see actually these past 40 years has been a time where we're getting an increased number of jamming. Let me just move this over. Okay. So the data that we're using, we have a hydrological model. We've got a paper out on that too, and also climate change runs with that hydrological model. We're using mesh for that. So the same model as the talk from the previous talk from here, using that. We've been using that quite successfully. Here are some of the data sets that we're using for the historical period, and also for the future period. We're looking at these data sets here, we were able to get some very nice results with that. If anybody wants that paper here, Burathoki et al. 2022, I can maybe afterwards put it in the chat if someone is interested. You know? Okay, let's move up here. We're using a delta change approach here. And then there's two ways you can actually look at this delta change approach. You can calculate a relative data, and you can also look at more of an absolute delta as well. Yeah. So the relative data is more of a percentage change. You can see here where the absolute delta values, you're looking at the simulated future values minus the simulated historical values. Yeah. And the relative one would just be more of a percentage here. And then for our future values, what we're looking at is looking at our observed historical values and adding this data delta here that we're calculating from our simulated values. You know? And here are some of the results that we have. These are now the discharges at Grand Falls. We can see here, this is our baseline here from the historical period, is the blue here. We've got now the future and two time periods here of each about 30 years, from 40s, 56, 41 to 70, and then the 70s, 80s, and 90s of this century. Yeah. It's more of the winter ones that we're actually looking at, yeah, for our midwinter breakup. So here, November, December, in January, February. We're not going to present that here, but also looking in March and April for our spring breakup and ice jamming period as well. And here are some of this is quite interesting. Here are the the flows of these are frequency distributions, yes. We can see that the probability of our flows are actually increasing over time. You can see here from the 40s to 2007, we have this line here where the probabilities of our return periods for our flows are to increase, and even further yet here for the last 30 years of this century. You know. Okay, what's a very useful metric too for us is the CDDF. That's the cumulative degree days of freezing. So this is from November to December. And basically what you do is you look at your average temperatures every day and you just add them up. Let's say if you start at 0 on the next day you have -2 degrees, the average temperature, your CDDF would be 2. And if, let's say, on the next day after that, it went down to -3, well, then your CDDF would add up to 5, right? So you can also see a little bit when it increases quite rapidly, you get more of a cold spell here. If it's slower, then it's maybe not as cold anymore. And you can see here how we have a certain bandwidth of these CDDFs. You can see currently now we have this blue here. It's actually a lot colder right now. This will actually now start to warm up. You won't have as many freezing days or nights in the future. Yeah, this has implications for ice thicknesses. Yeah, so your ice thickness will not be as thick. Yeah, which can then increase your probability of jamming when the ice is unstable and it crushes or it collapses. There is a threshold, though, that when the ice is too thin, that the ice will just crumble and just wash out and not jam. Yeah. So this is something that we still have to explore in this work, is to see where that threshold might be. Yeah. So you get a decrease in ice thicknesses, which can initially cause higher propensities to jamming. But the more thinning you have, there is a threshold where ice won't jam anymore. It will just tend to wash out. Yeah. So that's something that we still have to sort of look at and to perfect this modeling a bit.
Carl, sorry. Yeah, we are past time, but because we started a little bit late, maybe 1 minute just to wrap up if you can. Yeah,
I'm sorry, I'm a little bit, I'm not prepared. I'm just doing this on the fly because I thought you would be playing this video. Okay.
Yeah.
So I'm just sort of, this is, here, I guess the take-home message here that in the future, we are expecting an increase in the number of jamming, okay? But that's what I said before, we still have to look at the threshold of the ice thicknesses, where we have that threshold between jamming and just ice flushing out, okay? Okay, well, thanks, Shervan.
Thank you very much, Carl. Yeah, sorry if there was any mistake, if there was mistake from my side, but I didn't really see this presentation. I thought maybe this recording.
Perva told me that you would run the video, but it doesn't matter. It's fine.
Yeah, okay. I thought you will be running it anyway.
Well, I tried. I don't know what happened with the sound.
Yeah. Anyway, thank you very much. It was very interesting and sound presentation. I think we have a couple of minutes before we wrap up this parallel session, before the break and before the panel discussion. I see there was a lot of discussion going on in the chat. So if somebody wants to have a discussion on that, maybe, I don't know, John, if you want to say something, or Philip, or others, very welcome. We can keep the room open and continue the discussion. Is there any interest for the discussion? If not, we can close the session. Okay, so I would suggest that we close the session. Thank you very much for everybody who participated and for everybody who presented. It was a great set of presentation and insightful. I think there will be a 30-minute break if I'm not mistaken, and then after that the panel discussion. Actually 2 panel discussions. So thank you very much. I hope you enjoy the rest of the GWF annual science meeting. And I hope you have also a very good rest of the day. Thank you very much and bye.